we were doing in terms of the classification of aerospace structures on, we completed 4 different bases. The second half is what we will look at right now. The next classification basis is in terms of the type of material that you have. And the type of material again could be of based on these layers of the material. One is in terms of having either homogeneous heterogeneous material. So composite would come under the non-homogeneous category, and also hybrid constructions where you could probably be using 2 different metallic alloys in the same structural component joined to each other in certain ways, say welding or whatever. So typically again you have non-homogeneity. The scales of non-homogeneity also matter in terms of how the analysis could be done. I think we did this as part of another question that arose in terms of the difference between alloys and composites, even though both are essentially mixtures. We saw that depending on the scale of the constituent members of each of those mixtures, in one case the homogenization is much simpler. The other case also, in fact, even in composites we do an equivalent homogenization, as I discussed earlier, but we will go into the math of that a little later. So that's as far as variation from one point in the structural component to another point in the structural component is concerned. We're talking of spatial points over here. Now we are, if we restrict ourselves to a single particular material point, the properties could vary in different directions. So that's where you have the difference of isotropy and anisotropy. And somewhere in between, so if this is general anisotropy, you could have a special case, which is what is mostly used with composites, somewhere in between these two, which is orthotropy. So essentially you're talking about materials for whom, if you know the properties in 3 orthogonal directions, any other direction you will be able to determine the property with respect to those 3 properties that you have, as long as you know the angle along which the property is required in a new direction. So that's as far as that is concerned. So essentially what we have been probably exposed to in undergrad is mostly homogeneous and isotropic and also linear materials, by which we mean that the relationship between the stress and the strain, if you put the stress and the strain, as we discussed earlier, are essentially second order tensors, which can by virtue of their symmetry be put in the form of column matrices of 3 normal stresses and 3 shear stresses. So it becomes a 6x1 column matrix. We will write down those probably in a couple of classes from now. But once we have that, essentially the stress becomes a 6x1 column matrix, the strain becomes a 6x1 column matrix, and therefore the relationship between them is through multiplication by a 6x6 square matrix. And we'll look into various features of that in terms of its symmetry, etc. later on. But essentially what we are talking about when we say linear or non-linear is that because there are so many different connotations. When you say linear material, it could be dependent on the kind of problems that you're discussing at that point in time. So what we are focusing on purely is the stress-strain relationship here. So that stress-strain relationship, in other words, that 6x6 matrix, it could be fully populated even in a linear case, but just that it's all constant. So that stiffness is a constant. So stress equal to I'll just finish this, 6x6 matrix into a strain, which is a 6x1 column matrix. So this stiffness matrix is essentially a 6x6 matrix, which consists of constants, or you can look at its inverse, that is the strain expressed in terms of the stress, what we call as the flexibility or compliance matrix, which is the inverse of the stiffness matrix, and that is essentially again a set of constants. So that's purely the difference between linear and non-linear as far as the material is concerned, because this whole classification is in terms of material. I think I very briefly touched upon in the very first class. There's another type of non-linearity which is very critical, especially for aerospace structures, which is the geometric non-linearity, which is the strain displacement non-linearity, which is changes almost always needs to be taken into account. Whereas for most applications of materials in primary structures in aerospace, the linear regime will be good enough unless you're doing some kind of an accident investigation or some damage mechanics or characterizing materials for future application, etc., in which case you have to get into the nonlinear regime as well. More from a point of view of pure design and estimation of even some extent to even the detailed design, you may not have to venture into the nonlinear aspects. Yes, please go ahead.
Sir, when we are writing the stress matrix, initially what we do, the diagonal elements are normal stresses, sigma xx, sigma yy, sigma zz.
Yeah.
Others are tau xy, tau xz. Similarly here, tau yx, tau yz.
Yeah.
This, so far we have studied this.
Yeah.
But in case of composites,
Yeah.
the shear stress acting on one surface, I mean tau xy, will it be different from tau yx because the composition is different? So
Excellent question. So the question is whether we can, let's see. Can I just maybe I can use the other thing, right? Okay. Oh, is it? Oh, yeah, thanks. Thanks. Yeah, so what he was talking about is even in a 2D case, you have sigma xx and sigma yy. You could write the 3D case, but it suffices now to write these two. Let's say tau xy and tau yx. So almost always we seem to be assuming that these two are equal, and therefore this matrix, this 2 by 2 matrix that we have here, matrix. So his question is this valid for composites? Okay. Anybody would like to answer this question? It will be valid. Okay. Huh?
if isotropy is nearby.
Okay. So let's say you're saying that if there is isotropy, then it will be valid. And but composites are anisotropic, right? So okay. Any reason why you said that it is still valid?
The symmetricity comes from the moment balance when we take an element. So even if it's anisotropic or not, the moment balance has to exist.
Excellent.
So
Yeah.
the symmetricity probably won't be there in the strain equation if there is an anisotropy, but the stress has to be balanced.
Okay. Very good. So this whole property is based on moment equilibrium, right? So he is saying that moment equilibrium should anyway be valid irrespective of what kind of material you have, whether it is isotropic, anisotropic, composite, or any metallic alloy, it should still be valid. Does everybody agree with it, or is there anybody who disagrees with that? Or could there be an exception to this rule? Yeah.
But I think like we will be having the components of the stresses on other directions. Even if we take moment equilibrium, due to that anisotropy, we may be having stresses in other directions too.
Okay. Okay. So essentially, you might. Oops. So essentially, what we are looking at is, let's say, a 2D element like this, a small, infinitesimally small element, let's say of length x and y, and you're applying, let's say this is the x-axis, this is the y-axis, and so in the x direction you have essentially a sigma x, and on this also you have a distribution which is sigma x, and because it is a distance dx away from it, so you have a dou sigma x by dou x into dx. Okay. So similarly, you could have, because tensile is considered positive, so you have sigma y here, and you have sigma y plus dou sigma y by dou y into dy or delta y is essentially what you have there. So in addition, you have these shear stresses. So on the x phase, you have in the y direction, that is what we call as tau xy. So essentially what you're saying is the first subscript is the phase on which it is acting. The normal is in the x direction for that, so that is tau xy, whereas here you would have, let's say, tau yx. Now those also will have a variation with this, which is because of whatever is the change that is happening over here. So here you would have, let's say, x, and here you have tau xy. So this will be tau xy plus dou tau xy by dou x, right, into dx. Similarly, this will also have an additional component, which is dou tau yx by dou y into delta y or dy. Okay. So it's essentially the equilibrium between these that we look forward to at least, and then take the limit. So usually instead of dx and dy, you would take delta x and delta y, and in the limit you would tend delta x and delta y to 0. Then you get into the differentials, and so the higher order terms will all drop off, and essentially this leads to tau xy is equal to tau yx. So how you do it is you take typically with respect to some point, the easiest point to take on this is this particular point, because these are all the complicated stresses that are there. So if you take the moment about this particular point, then the moment arm of all of, especially of these two, the sigma y term over here, and also the this sigma y term over here and the sigma x term over here, they will not cause any moments, and you will take the moments of all the others. Then you tend delta x and delta y to 0, and essentially you will end up with this. Okay, so that is the basis of what he was saying, just the mathematics behind that, right? Now, is there some assumption that is involved here, or something that makes this not always valid? This is valid for most situations, and in most situations, even in aerospace vehicle applications, even when there are composites. So this is valid because this is independent of the material. So what we are doing is purely a dynamic equilibrium equations that we are setting up purely from Newton. And irrespective of what material this whole element might be made of, it doesn't matter. It doesn't matter, and you would still have the same equilibrium equation still valid. But are we missing something over here? Is there a possibility that this can sometimes come under question? If so, what? Fluids, okay. What could be the reason why it happens so in the fluids?
There's no moment balance.
Okay, okay. Okay, okay. Okay, okay, good point. So let's keep that aside. Let's restrict to solids. So in solids, is this always valid? Okay, very good point. Yes. So high strain rate cases, what would happen?
Because in that there is because the non-equilibrium is what causes the motion of any element. So that has to be equated to the change in the rotation of the element. So there this may not be one.
Yes, very good point. So there is a possibility that when you have very high strain rates, the stress, because it varies with the strain, there is a possibility that that can be flouted. But let's say it's a statics problem, solid under static loading. Is there a possibility that this can sometimes not work, this equation? Okay, so let's see. I didn't go through all the steps, but I'm sure all of you are familiar with that. This whole process of calculating the equilibrium, moment equilibrium about this particular point, the moments about a direction which is perpendicular to the screen, and you will end up with this particular equation. So have we taken into account all the stresses and or possible forces and moments that are there in this particular problem, or is there some assumption involved where we have probably dropped off something? Very good. So the forces have not been taken into account. So let's say, for example, the weight or something like that. So that will have not only at, though we might draw it at the CG. So essentially it's a distributed force, and the moment due to that has to be taken into account. But the very fact that the way we define the CG, it takes care of that. So even when there is a body force distribution, you would still have this valid as far as the moment equilibrium is concerned. But the body force will definitely affect the force equilibrium equation. So the force equilibrium will be affected. So you're very close. You're heading in that direction.
Uniformly distributed still?
Yeah, it will still happen. Yeah. It will affect the distribution of the force equilibrium equations, okay? But it will not affect the moment equilibrium equations.
So if the mass is concentrated on one side,
Uh-huh.
then CG will be shifted towards the more mass.
Okay, okay.
Then we will get moment of weight.
Okay, okay. So that's essentially what she is also talking about, the mass distribution being different in different locations. So you would essentially have that. There's also another way in which you can put it. If it's a very large structure, let's say, experiencing the gravitation field of more than one bodies, and the acceleration due to gravity itself could be different at different locations. So those are two different ways of looking at it. But just like body, you talked about body forces, there is a possibility of what are known as body moments, which people don't usually address, because most materials are not having these, and even if they have, the values of these are so negligible that this might not be there. But we will see later on, probably I removed the slide, but one of the materials that we'll be looking at, or typically is looked at as an option for, especially for actuation and or sensing, are magnetic materials, magnetostrictive, magnetorheological materials, etc. And those typically have some kind of a dipole moment distribution within that, and that creates a certain resultant moment. Just like you have a body force over here, you have a body moment as well. That is a possibility, and that body moment has to be accounted for in this overall moment equilibrium calculation. So there will be a difference which is essentially depending upon that body moment. Let's say we call it some m0 distribution. So that m0 in some sense will affect that difference between tau xy and tau ix. So you can just think of it. So essentially what are we doing? How did we arrive at this equation? We're just setting the moment equilibrium about this point. In other words, we are taking the forces due to all of these stresses, multiplying by the area on which they are acting and the moment arm, and then adding up in an algebraic or positive, some negative. So you're adding them up in algebraic sense, and then setting it equal to z in the limit as delta x and delta y tend to 0, you would see that this essentially happens. But in the same moment equilibrium equation, if this m0 were non-zero, then what you would have to do is that you would have to take that also as one of the terms in the moment equilibrium, and that is what will essentially appear here with certain, obviously the dimension has to be right. It's not just m0 here, but a term which is dependent on m0 over here. The reason why, so as you said, your the body forces can also even contribute when you're talking about it in a finite sense, but eventually we are bringing it to a point. So in the limit as delta x, delta y tend to 0, so those will typically be higher order terms and will drop off. But so it's a very good point, because that gave insight into understanding this, that these are two different types of almost everybody is familiar with body forces, the simplest of them being gravitation, which is experienced by all flight vehicle structures operating in the gravitational field. Whereas this is usually ignored, and for the right reasons, because it's a very rare situation where you have magnetic materials, for example. There could be other potential materials where and again, of course, it's not just the material, but also the field in which it acts. The body force, even though a particular structure has mass, it might not have a weight if there is no close by body which exerts that kind of pull. So not only a body with a non-zero mass, but also a gravitational field in which it is present, so that the body forces are there. Similarly, for the body moment to be present, when I talk of a magnetic material, it has to be in a certain magnetic field. Otherwise, it may or may not have an effect on, it may not be present, and therefore will not affect this particular equation, right? So I think that answers your question, right? Yeah, so what were we talking about? Yes, linearity, non-linearity. Then another basis for classification on material type is elastic and inelastic. And within inelastic, there could be many different types. One very standard example that is used is plastic or elastoplastic, etc., essentially moving away from elastic in some graded fashion. And so we will be focusing mostly in this course on linear materials, elastic, but here we will be looking at non-homogeneity and anisotropy, because composites are essentially that. But there are ways in which we can overcome that. I already gave you a hint that in between these two, there's a concept of orthotropy, which we will take advantage of. There's also a concept of what is known as transverse isotropy, which we'll take advantage of. If you have not heard of these terms, don't worry. We will very specifically define those as we go later on. Now, between these, again, yes, composites are non-homogeneous, but as I said, we will do what is known as a micromechanics study, where we will get into an equivalent homogeneous material I referred to last time. It's an imaginary material which has different properties in different directions, but it is essentially homogeneous, and that artificial material will be replacing this as far as the mathematical model is concerned, and everything will work, except when we want to understand the damage mechanics, etc. You have to go back to your original discretized model where the heterogeneity is there. And then, so how you typically do is, if you try to do it as fiber and matrix for an entire structure, even with the best of supercomputers that you have, it will be an unmanageable problem because of the length scales that are involved. The fiber diameters are of the order of a few microns, let's say about 10 microns, and you have a structure which is of the order of 10 meters or so. You can see how many different fibers are there, how much matrix is there, how many interfaces are there between the fiber and the matrix. Becomes an unmanageable problem even with the best of the hardware and software that we have. So it makes a lot of sense to do an equivalent homogenization and apply the problem to that. But if you are interested in, let's say, the damage mechanics, especially, let's say, the matrix cracking or fiber matrix debonding in particular, for example, you do need to understand the fiber stresses, the matrix stresses, the interface stresses. So to do that, what we typically do is, for the overall structure, let's say this tabletop I'm analyzing, I will do and it's made out of a composite. Wood is a composite. So I do the analysis with an equivalent homogenized material, and there's a particular place that I'm concerned about where there is stresses are large. From that analysis, I found out a particular location the stresses are large. So I'll take a small structure there, what is called as a substructure. So essentially, it's of the overall structure, it's a subset, and therefore it's called a substructure. And then you do what's known as a substructure analysis. And for this substructure, you have the boundary conditions for that from your original analysis of the entire structure. So from that, you know the stress distribution, the displacement distribution in the entire structure. So at the boundary of this substructure, you know the boundary conditions, both in terms of the displacement field and or stress, whichever is convenient to you. You can apply it in a particular way or combinations of those. And essentially, you're then in that substructure, you go back to the original material. That is, you're no longer dealing with a equivalent homogeneous imaginary material, but the actual fiber and matrix distribution over there. And that is a more manageable problem depending upon the size of your substructure. And then you can find out the actual stresses in the fiber matrix and to find out whether the debonding will happen between them or not, or at what level of the overall loads you will have that happening. So you can make conclusions based on that. Okay. So that's as far as this is concerned. So, so what I was essentially telling is that we will do non-homogeneity, we will do anisotropy, we will take them into account, but there are ways of working around. We will not take them into account as it is, but workarounds which are engineering workarounds, which are valid workarounds, is what we will do. And because under most healthy structural conditions, you would have still the material operating in the linear regime. So we'll look at linear elastic materials. So in other words, I was earlier talking about this column matrix. You have a 6x1 stress related to a 6x1 strain through a 6x6 stiffness matrix. So if you're talking about in terms of that, what this difference essentially means is that stiffness matrix, 6x6 matrix, the elements that it has, they are going to depend on, if you move from one point in the structure to another point in the structure, that matrix can change. It is a possibility that it can change if it has gone to a different domain. What this essentially means is that there can be a difference. For typically, when you're considering an isotropic material, for example, he talked about the diagonal elements. So the diagonal elements associated with non-stress equal to the diagonal elements associated with the shear stress and shear strain would all be equal to each other. That may or may not happen in all cases, and therefore that difference will be accounted for in over here. So the same thing, one we looked at it from a physical perspective, now we are looking at it from a mathematical perspective of that stress relationship and what happens. Now, in terms of the difference between these two, can anybody say, in terms of the stiffness matrix or the flexibility matrix for that matter, what would be the difference between an elastic and an inelastic material?
The stiffness matrix for an elastic material will not depend on the stress, but for an elastic material it will be dependent on the stress or strain.
Right. So that's one way in which linear and nonlinear materials are. So the linear and nonlinear, the linear material will have a stiffness constants, which are all constants really. The others will have the elements of the stiffness matrix as functions of the strain. If you're expressing stress in terms of strain, that's the stiffness matrix. If it's a flexibility, the inverse of that, they would all be functions of stresses. Okay. Instead of saying they would all, in general, those elements would be functions. Some of them could still be constants, but even if one of them is not a constant anymore, then you have the difference between linear and nonlinear, right? But what is is it at all possible, first of all, to have a stiffness matrix in the case of inelastic materials?
Stress will not be linearly related to strain.
that is still going to this. So these are two different things. It can be possible that you have a nonlinear material which is still elastic. Okay, so let's not mix up these two aspects. So this is one aspect that is covered. We are saying that in this case, all the 6 by 6 elements, that is the 36 elements of that matrix, would all be constants. Here, at least one of those 36 will not be a constant. It will be a function either of the stress or the strain, and therefore we are saying it is nonlinear. So essentially, the relationship between one of these stress components and the strain components is no longer proportional. It is having some kind of a further functional dependence. So in other words, we plot the stress versus the strain. It's not a straight line for all of these 36 plots that you can have, and some plots are having curves instead of straight lines. So that's essentially what we are talking about there. So what are we talking about here purely in terms of a stress-strain relationship? Yeah.
Actually, if we think about elastic materials and plastic materials, if we try to differentiate between them, first thing, if we look at the strain of them, if we give, if the material is loaded within their elastic limit, we see the strain. Then if you unload it, it will come back to its original shape.
Right.
But in case of plastic, that thing will not be there. I mean, if you talk about simple stress strain curve of steel, they have a large plastic region where there is no possibility of coming back to the original position. So there may be materials where we can have non-linear curves are there, but they can be elastic in nature.
Yeah.
When you talk about concrete also, they have a parabolic elastic
Yeah.
curve.
Yeah, continue.
Even in the plastic, we are able to demarcate between like for materials like viscoelastic material or bingham plastics. They have the characteristics are there, so we can definitely plot.
Okay. But yeah, but is important. What follows that?
We should be ascertain about what nature it is following plastic.
Okay.
Define
Right. So because we are generally saying inelastic, that means it's not elastic. There's many different possibilities of what could actually happen. But what is the thing that is valid for elastic, which becomes invalid when we go to inelastic material, purely from a stress-strain relationship? Is that is what we are trying to look at. Right? Okay, so what we said is that essentially writing the as the normal stresses, let's say sigma xx, sigma yy, sigma zz, sigma yz, sigma zx, and sigma xy. Okay, so this is the typical order in which it is written. So essentially, what we are talking about is a 6 by 1 column matrix that we are representing it by, taking advantage of the fact that the shear stresses are complementary, assuming that there are no body moment distributions in the material that we are considering. So therefore, only 3 of the shear stresses need to be considered. Sigma zy need not be considered separately. Similarly, xz and yx also need not be considered separately. And similarly, you have the, let's say, gamma, which is the strain. Again, oops. So it's your 6 by 1 matrix that you have here, which is consisting of, let's say, gamma xx, gamma yy, gamma zz, gamma yz. Okay, so if you don't remember this order, it's typically the first one x is missing, and then you go in the cyclic order, x after x what, y and z, and then you change that in a cyclic manner. Y becomes Z, Z becomes X. Similarly, Z becomes X, X becomes Y, okay? So it's a convention that is used. You can always jumble it up, but of course your stiffness matrix has to be jumbled up in an appropriate way, and you have to follow the entire derivation in a consistent way. But this is a standard convention which is followed in a lot of textbooks and research papers, etc. So it's good to stick to that. So essentially what we are saying is that if we relate this sigma and gamma, so we are saying that sigma is equal to some stiffness matrix, which is a 6 by 6 stiffness matrix into your gamma. So that's essentially what you're talking about, okay? So now we are talking about the various differences there. One is in terms of the material. We talked about homogeneous material. All that we are saying is that S, the 6 by 6 S matrix is so the spatial coordinates are not directly affecting your values of any of those 36 elements of the stiffness matrix. So that is essentially what we mean by it's an homogeneous material. And isotropic, essentially, as we said, you would have the first three diagonal elements which are equal to each other, because the way the between sigma xx and gamma xx, same way this behaves, etc. There are two other things that will come across, but essentially what we are saying is that at any given point, remember all of these are point functions, okay? So these, each one of them in general is at a particular point in the entire structure, that you identify a particular material point, and at that material point this is essentially valid. At the adjacent material point, the stress could be different, strain could be different, and if the material is different, S could also be different. That's what we call as a heterogeneous material. Whereas here isotropic, we are having certain simplifications in terms of the independence of the 36 elements that are there. So not all 36 elements are independent, right? Of course, it's much more simpler than that, but essentially you're moving towards reducing the number of constants that need to be determined here, because typically this needs to be determined experimentally, okay? So for any given material, you typically do certain standardized tests in order to plot your sigma versus gamma under certain specific conditions. Some elements of gamma and or sigma are maintained 0. The others are allowed to change, and then you plot one against the other, and based on the slopes, etc., you actually come up with populating this 6 by 6 matrix. So the number of tests you need to do and essentially arrive at that will become much, much lesser when you move from an anisotropic material to an isotropic material. So that's essentially what we are talking about there. The other thing we mentioned is linearity, by which we mean that your sigma, so essentially it is this. So it is this relationship is valid. Every 36 elements of that matrix are constants, okay, vary with respect to anything. So nonlinearity means that yes, so essentially this condition is violated. So at least some elements of S, let's say some particular element Sij is no longer, okay, it varies with gamma. So if gamma changes, then there's a possibility that at least one of them, so at least one amongst the 36 Sijs that are there will vary with at least one of the 6 gammas, that is the strain elements, and therefore you're talking about linear. Now, the question because of which we came to the board is, how do we similarly define elastic purely in terms of S? Because here we defined homogeneity purely in terms of S, that it is not a function of X, Y, Z explicitly. Similarly, isotropy, we are saying something about the 36 elements of S. So everything we are defining with respect to the stiffness matrix S. Okay, linearity, we said that S is a constant. Can we say something about elastic case, that in terms of S or in terms of an equation like this? Yeah, so that's one of the qualities of, let's say, an inelastic material, that when the loading is done and the unloading happens beyond the elastic limits, then you end up with residual strain. That's correct. So how does that reflect on the relationship between sigma and gamma? So I'm essentially talking about this particular relationship between sigma and gamma. How does that change when a material stops being elastic? That is already taken care of here, right? So that's linear. So because this is a very standard mistake a lot of students make, confusing between linear and elastic. In terms of definition, they might come up with, but sometimes they associate that if a material is linear, it's also elastic, or if it's elastic, it is linear. It's not necessary, okay? So what you have told about in terms of the properties of inelastic materials are all correct, whatever each of you has said. But how does it reflect in terms of a sigma-gamma relationship? Still, that comes under this. So essentially what we mean by Sij varies with gamma is that if you expand that out for that particular sigma term, let's say sigma xx, you could have one of these appearing as a square, etc., right? So that's essentially what it's two indirect ways of saying the same thing. One, you are writing in terms of matrix equation and saying that coefficient matrix is a constant or not a constant. The other is when you're expanding that out as scalar equations instead of these one single matrix equation, you're putting it as 6 scalar equations, and some of them can have terms which are not linear, could be quadratic, as you said, right? So that is true, but that is still under this domain. This is different. Plus what? Examples? Plus some stress. No, because if it's still in plus some stress, what you're talking about is still, you can rearrange those terms to take all the stresses back to your left-hand side. Essentially, what you're arriving at is a possibility of non-linearity, right? So it's still not elastic. Yeah? Okay, good. What about the strain energy?
Basically, adding, but again, we cannot express it in terms of metrics.
Wait.
There is a term that has both sigma and gamma, and it cannot be isolated to write an equation.
Yeah, so you're saying that it cannot be an equation which will be inverted. So you essentially have, you cannot write one in terms of the other. It will all be jumbled up, right? So you can't solve for all these stresses in terms of all the strains. That still comes under the nonlinearity aspect. So it still is not elastic. There is something missing there. So.
Sir, we have the force displacement relation, like F is equal to Kx. In an inelastic material, this relation might not hold and stiffness matrix K might not exist.
Good. Okay, so that's a very good question. And F is equal to Kx is just talking about in terms of relationship between the loads and the displacements, right? So this is essentially the material contribution towards that. So what you refer to as K there is essentially relating the force to the displacement But in building that up, K up, this has one of the primary contributions from the material. But there are additional contributions coming from the geometry also. That is how your S and K are different from each other. But what you told is absolutely right, that K may not exist in such a situation. Why doesn't a K exist in such a situation? What is it about inelasticity that makes K non-existent in certain cases? Of course, there are workarounds and you might still be able to come up with it, but essentially the way we define K purely from relationship between F and S, or F and U, let us say, rather, you will not have that K existing, right? So what is it essentially from a mathematical point of view? What can you say between the relationship between sigma and gamma that is getting violated, because of which either K doesn't exist or equivalently your S doesn't exist?
So whether sigma and gamma becomes independent in case of inelastic?
No, they still depend on each other. So for example, if you, typically plot, as she was mentioning, you have let's say a sigma versus epsilon. You go up to a certain linear regime, and then you go into non-linear and the inelastic regimes. And when you unload, you could probably you end up with a strain which, let me use consistently. I just want to use the consistent notation with that instead of epsilon gamma. So essentially what you're saying is that while you're loading, while unloading, so that there is a remnant strain that is over there, right? So that is essentially what is happening in that case. So, but is there something that is specifying about this relationship between sigma and gamma that is complicated in the case of an inelastic material? What is that complication that is coming about? Very good. That's essentially the point. So essentially what you're saying is that either for a particular value of stress, there can be multiple values of strains, or for a given value of strain, there can be potentially multiple values of stress that are possible, right? So that essentially means that there's the one-to-one correspondence between sigma and gamma no longer exists. So it gets violated, and therefore what we are saying is that sigma depends not only on gamma but could depend on something else. For example, the history of what happened before that particular point in time. So whereas this relationship up to whatever we were considering, even if it is nonlinear, even if it is non-homogeneous, even if it is anisotropic, you give me a strain at a particular point, I'll be able to tell you a stress at a particular point as long as I know that the material is elastic. But once you tell me that it has gone into the inelastic regime, I cannot give you a unique value of a strain or vice versa. So essentially, it is starting to depend on something more than, the stress is starting to depend something more than the strain. In the nonlinear case, instead of putting it as Sij varies, you could also write this whole thing as sigma is equal to some function sigma of gamma, right? So that need not be a linear function, whereas here it is a linear function over here. It could be any arbitrary nonlinear function. This is still elastic. It could, whereas when you go for an inelastic material, what happens is your sigma is equal to sigma of gamma and something else. So yes, definitely. So time explicitly could make an impact over there. And why that time makes an impact is essentially because the history becomes important. But it may not only be an explicit dependence on time, it could be something else that is essentially happening. So essentially this one-to-one correspondence is not there, as he rightly pointed out. So it's extending it in a more mathematical sense. So any questions on this? Okay, so let's continue what we were doing. Oops.
So does this mean that if a material shows a quadratic curve but still has a single value of stress and strain, we could call it elastic?
Come again, I didn't follow that.
Like if a material has a quadratic variation of strain,
Stress versus strain, yeah.
would we still call it elastic?
It could be. It could be elastic or inelastic just by that information alone that you give me, that one particular sigma, let's say some particular sigma ij is varying with respect to some other gamma kl. It could also be the same set of subscripts, but let's say some sigma ij with respect to gamma kl is a quadratic relationship. Purely from that information that you give me, I cannot make a conclusion whether this material is elastic or inelastic. But I can tell you for sure that this is a nonlinear material. It could be either a nonlinear elastic material or a nonlinear inelastic material. That I will not be able to tell you. But what it means is that, yes, with respect to the strain, it is quadratic means that if you are also implying that it doesn't depend on anything else, given the strain I'm getting the stress and it's quadratic, then yes. So then it is an elastic nonlinear material. But purely based on that, because you might have controlled conditions in which you're estimating this curve. So typically you get this curve through an experimental test. What are the things that you have kept constant, or what are the things you're controlling in your boundary conditions, the loading conditions, the support conditions, and the specimen, etc., so that you get this particular equation. So I need all that information to ensure that the stress is not a unique function of the strain.
But in general, like, I mean, for the Hooke's law and all,
Yeah. Right. Yeah. That is understandable, because essentially what you're saying is that if you have one particular sigma ijm plotting versus gamma kl, you're saying that it is linear. So then there is no possibility within that, when I load and unload, it has to come through that. So there is if I know in a particular range it behaves only linearly, that is probably the only way in which it is, and therefore it is also elastic. But it need not always be the case. That is essentially trying to hit. Okay? Because each of these terms has some very precise meaning. They're very simple terms, but unless and until we understand them appropriately, we could make errors. And it's important to be very, very precise, especially when you're doing some research or writing papers, etc. Yeah.
Sir, there's a relation between Young's modulus E, G on the bulk modulus, Poisson's ratio, and K. So if K and the stiffness, one of these is non-existent for one particular material, then it is going to affect all other constants which are having, the relation between E and K,
Yeah.
relation between K and G,
Yeah.
all are going to be different, or
Yes.
how it will be.
Yeah, it's a good question. So essentially you're talking of, let's say, the shear modulus, which for an isotropic material is given by E by 2 into 1 plus nu. What is K given by? 3. One minus 2 nu into, no, I think it's in the denominator, right? Okay. It's correct? Yeah. So this is what he's referring to. First of all, remember that this is valid only for isotropic materials. Okay. And in isotropic materials, so what he's talking about is essentially there's a possibility for some material that either G or K does not exist. Okay, so when can that happen? Essentially, this is blowing up, right? So you're in the case where the Poisson's ratio tends to, in the limit as Poisson's ratio tends to -1, essentially your G will no longer exist. And in this case where the Poisson's ratio tends to +½ typically you will have a situation. So for isotropic materials, therefore, you say that this is the range for your Poisson's ratio. It cannot be less than -1. It cannot be greater than half. This typically is what you call as an incompressible material, because your K moving to infinity essentially means that it doesn't change volume, right? So because this is a measure of, for a given amount of pressure, how much of volume change occurs, or in other words, for a unit volume change, how much of pressure I need to apply. So it's essentially talking about that. So whereas that is, so here what we are talking about is some kind of a pressure distribution that you are having, some P, for which there is a change in volume from the original volume V to, let's say, V plus delta V. And essentially you're saying that whatever the value of P, your delta V or change in volume is essentially equal to 0. Whereas here, what you're essentially saying is that you have a pure shear case. And when you're applying this shear stress, there is a change essentially in how, in the angle of the 90, whatever is originally 90 degrees is undergoing a change in both directions. Of course, I've drawn in only one direction. But essentially what is happening is that change in the right angle is what is your shear strain. But what you're saying is that when G goes to infinity, how much ever shear stress you apply, however large your tau xy might be, you would still not end up with any gamma xy, that is essentially strain. It's rigid, or it is inflexible in shear. That is essentially what you're saying. So these are the two limits that you can have. But as I said, this is valid only for isotropic materials, and composites are not isotropic. So you could have situations in which certain Poisson's ratios in certain directions, because remember, only for isotropic material, Poisson's ratio is a single constant. For composites, in different planes, you could have different Poisson's ratios, and some of those in certain planes can go less than -1 or can even go above half. But still, there are upper and lower limits for that. And there are ways in which the upper and lower limit can actually be derived. But there is a possibility that this particular thing is violated. This is purely coming from this relationship where you see how the G is dependent on the Poisson's ratio, how the bulk modulus is dependent on the Poisson's ratio. Sorry, I forgot your question leading to this. Correct, correct. Yeah. Yeah. Yes, yes. So it's, in fact, just as I mentioned, that this limit is for isotropic. Similar limits can be derived for the composite. If you go to that limiting value, then something similar can happen, that you end up with something which is rigid in shear, or which is incompressible kind of a material. So that is a possibility that is there, theoretical possibility in a composite also. Okay, you don't have specific values that you can generically say this is the value that it should not exceed. It will depend from composite to composite. The volume fraction of the fiber and the matrix for the same composite can also alter that limits of the Poisson's ratios. And it will be different limits in, as you just pointed out, in different planes. because it's essentially a planar relationship that we are talking about. The Poisson's ratio, you're applying stress in one direction, in any particular orthogonal direction, you're trying to see the strain effect on that. So the relationship between those two strains, one is the direct effect, the other is the indirect effect. The ratio of that with a negative sign is what you define as the Poisson's ratio, right? So the choice of which direction you're loading and which direction you're measuring, even if you invert that, instead I load in this direction now and measure in this direction, then also the Poisson's ratio will change, okay? So in fact, it always does. So that isotropic plane, where the plane itself perpendicular to a fiber, let's say all fibers are going in one particular direction, what we call as a unit composite, and in a plane which is perpendicular to that, it's like an isotropic plane, because what direction you take is perpendicular to the fiber. Any arbitrary direction I take in that plane, it's perpendicular to the fiber. In that plane, there is a semblance of isotropy, what we call as transverse isotropy. This is a longitudinal direction, any direction perpendicular to longitudinal direction, transverse direction. So there's a transverse isotropy that is essentially representing over there. Some of these kinds of relationships would still be valid, but any other arbitrary composite, you would typically have you would have limits, but you would have different planes. Yeah. So let's skip back. Yeah. So I think we finished that. So another way in which or material based on material types, aerospace structures could be distinguished is in terms of unifunctional materials and multifunctional materials. So unifunctional, essentially talking about load bearing as its function. So that load bearing means it has to offer certain strength, stiffness, and stability for any kind of loads that it is designed for. And that is essentially what we call as a conventional material, whereas the multifunctional material, it offers some additional functionality over and above load bearing, over and above strength, stiffness, and stability, some other functionality it offers. And within that multifunctional, one example is smart materials. So it's not that anything which is not conventional smart. Smart is an example of a multifunctional material where that additional functionality over and above load bearing is essentially sensing and actuation. So an ability to adapt to the environment. That's why these materials sometimes are called as adaptive materials. They adapt to the ecosystem as there is, let's say, the temperature changes or the pressure changes or some kind of other parameters, let's say even the mechanical load changes. There's some way in which it senses that, and based on that sensing, it changes its behavior or its material characteristics, so that in that sense it is smart. So within that, again, there could be many different types. There could be what are known as SMAs or shape memory alloys. These days there are lots of shape memory polymers also, SMPs. Then there are piezo materials. Many people use them as wafers, but there are also piezo films. Again, very common, especially PVDF film, for example, used as sensors in many different applications. Then piezo ceramics. So typically, and piezo ceramics usually used as actuators. And then there are what are known as piezo fiber-based composites. So in other words, just like you have in a difference between a metal and a composite is that you are having long fibers along which the properties are superior, greater strength, greater stiffness compared to the other perpendicular direction. Similarly, in a smart material, the purpose of that is to be able to sense and actuate. So the way you measure that property is its sensitivity and actuation authority. So how quickly it senses things, how small values of change of any particular parameter, and how it responds in terms of what kind of forces it can generate, etc. So in that sense, these are kind of the cutting edge right now in terms of the possibility of piezo materials As you know, the word piezo itself, the prefix refers to pressure, essentially a mechanical load, and electric, saying that there's a coupling between the electrical energy and mechanical energy can transform from one to the other. So that's essentially what we're talking of piezo materials. But piezo composites are those where each fiber is essentially a piezoelectric material, so that if I extend that, it also generates an electric field, or if I input an electric field across that, it can change its length. And essentially that change is much more than when you have it as a bulk material, as a bulk piezoceramic material. Let's say the same from the same piezoceramic you're trying to make a piezo fiber. There are two ways in which it typically is done. The way it was first invented was through an extrusion process, where you have these ceramics extruded and therefore you get circular kind of cross sections. But those processes were very expensive for piezoceramics in order to make such circular fibers, though it had superior properties. This was actually invented by MIT, and then NASA came up with a way to economize on this, the same almost close by properties, but much cheaper to make. What they took is they just took a plate of piezoceramic and they used a dicing saw to dice it, so that you now have fibers which are no longer circular, but they are square or rectangular cross-section fibers. Because of the square or rectangular cross-section, they have slightly inferior properties compared to the circular, but a huge reduction in the cost. So it's very important. The reason why I'm specifying this example is that it's very important for engineers to think from the perspective of costing as well. It's not just in terms of an improved model and things like that, because eventually all that is driven by the economy and how it affects the overall economy or particular company's economy, etc. So in that sense, you would see that piezo composites by themselves are great compared to many other piezo applications, but within piezo composites, a less expensive option is to have this kind of a way of manufacturing the piezo fibers. Then magnetostrictive, magnetorheological, electrorheological, etc. We will not venture into all that. There used to be a course, I don't know if it's any longer taught in the department, related to smart structures, but there's a lot of research which goes on in the department. Many of my colleagues, as well as we at our lab, work on a lot of these kinds of materials. As I said, smart material or adaptive materials are only one example of multifunctional materials, where the additional functionality other than load bearing is sensing and actuation, usually in a co-located sense. When you say co-located, means the same material is able to do the sensing as well as the actuation at different points in time. You can use it as a sensor and as an actuator. So essentially, because see, this conversion between electrical energy and mechanical energy is two-way process. You can reverse that process. So when you're using it to, let's say, input electrical energy and getting a mechanical output out of it, you are using it as an actuator. When you're inputting some mechanical load to it and therefore measuring the electric field that is generated, you are using it as a sensor. So the same particular set of material points can be used both as sensor as well as actuator. As I said, that is one additional functionality. There could be many others, like electromagnetic properties that you can bring in, or energy storage, etc. So imagination is the only limit there in terms of what all possibilities are there, but many of these are still in research stage. A few are being tested out on certain prototypes in some of the R&D works, both NASA in the US as well as in Europe, and a few examples of what we have tried out in India, also in HAL, for example, for the Dhruv advanced light helicopter. One of the initial prototypes, there was a fatal accident, and they about 20, where we tried health monitoring system for the tail rotor, so that the pilot gets in with the simple onboard computer. There can be an advanced warning of there being a launch crack or something that is occurring in the tail rotor flex beams, that a corrective action or a immediate landing can be effected. So it's something that has been around for a while, but in terms of large scale applications, still there's a lot of stumbling blocks. One, of course, is the certifying agencies. The other is many of these materials are very heavy. Though you're not going to apply it on the entire structure, you're going to be using it only here and there where this is going to make a huge difference in terms of the performance or the health monitoring or some particular specific application, but still the weight penalties are fairly large, and the range in which they operate, etc., sometimes are kind of limiting, and therefore you might have to go to multiple systems. So there's a lot of room still to do a lot of research into this, though this whole subject area has existed for a few decades now. Then maybe I'll complete with this. The external load type, based on that, how do you classify? We will revisit this in a little more detail in the next class, but essentially you know the kind of typical loads that we need to be concerned about. One is the gravitational load. And especially, of course, in the case of aircraft and things like that, the range of that, the variations are not much. But when you are looking at spacecraft, etc., this plays a very, very critical role from multiple bodies. So you need to take that into account. Then the inertial loads, essentially the D'Alembert's force, what you call as the mass into acceleration. Here, whenever we talk about a load or a force, we're talking generalized sense, we include moment also. So an inertial also in the inertia multiplied by the angular acceleration, rotational accelerations that might be involved. So and another case where inertia plays a critical role is gusts, because typically it's measured in terms of the n values, the load factor, how much it changes by a delta n due to a gust, and that is typically how certain gust ranges are defined for any new aircraft to be tested before it can be certified. So over and above your VN diagram that we talked about in the previous class, you would have to give room for typical gusts in the typical kind of conditions that it flies. It also depends on the altitude at which it flies. Even if it's very large altitude, it has to go from the ground to that altitude, so it has to fly through the other altitude ranges, so it has to be certified for the possibility of gusts closer to the ground as well. Then another very important load, of course, is the thrust coming from the engines, depending upon the number of engines you have, how you have distributed that. Sometimes there can be thrust vector controlling, where you can change the direction of your nozzles of the exhaust of the engine, and therefore you can direct the thrust. Also, though most of the control is essentially affected using the control surfaces, the rudder, the elevator, and the aileron, sometimes you could have differential thrust in the engines in order to effect certain maneuvers over and above whatever you can get with the control surfaces. So all of that is important. The engine, apart from the thrust, will also have its self weight. So that where, depending on where it is attached to the rest of the aircraft, the pylons, you will have to look at that load as well. Then exhaust turbulence can sometimes become an issue. For example, if the engines are mounted on the wing, and in the wake of the engine exhaust is the tail, your horizontal and or vertical tail, and they could be phasing that turbulent air, and therefore burnt air, and therefore you should account for the kind of loads that come because of that as well. And that includes not only the mechanical loads because of the turbulence, but also the fact that it's an exhaust and higher temperature typically. So you need to have the thermal loads analyzed for that situation as well. Then, of course, the mechanical loads, in particular the landing gear while taking off and landing. So the friction between the tires and the tarmac of the runway, then how that contact mechanics of that gets eventually translated through the landing struts to the aircraft. So all of that is important. Another example that we already considered are impact issues like bird hits and or let's say a mechanic dropping a tool, etc. So those kinds of impact loads, those all come under mechanical kind of loads. The most important, of course, the aerodynamic loads. In particular, the lift is the dominant load, and over and above, and then after that, pitching and which are rolling moment and the yawing moment, and sometimes a sideway force as well, because of which there could be a drift that is happening, which all minor things to be accounted for. So the aerodynamic loads are essentially due to the pressure and shear distribution of the interaction of the fluid flowing around the air, the speed of the skin, and what is the shear that is happening because of that, and what is the pressure load, and what's the difference between the pressure integrated over the top surface and bottom surface, or the rear and the front, for your pressure drag, for your skin friction drag. If it's a supersonic or even transonic for that matter, there could be certain regions where wave drag could be important. So all of that will come under the aerodynamic loads. Then you have we just gave an example of a thermal load. There could be other possibilities of thermal load when you're designing the structure of the engine components itself, especially in the combustion chamber and the nozzle and in between the turbine and the turbine blades, etc. Then there are loads coming from the control surfaces, and depending upon what kind of control surface it is, there is a way in which the load is transmitted from the pilot to the control surface. It could be electric, magnetic, hydraulic, pneumatic, whatever, or sometimes you have combinations as well. And then, of course, eventually that comes as part of the aerodynamic load, because the control surface is deflected. Essentially, your overall airfoil cross section is changed, and because of that, the aerodynamics of it changes. The lift distribution, the L by D, etc., the other things change as well. But essentially, going forward, it is all your 4 core courses that need to be combined. Whatever you're studying as part of your fluid mechanics, whatever you're studying as part of your thermodynamics, propulsion, then the navigation, guidance, and control, and what you're studying as part of this course, flight vehicle structures. And that's why this is almost a standard field in most aerospace industry, especially the large ones, where they need to do this study, because, as I said, each one of them is so advanced today. There was a point of time where there was not enough knowledge about each one of these fields, let's say about 30-40 years back. Then people were doing a lot of deep research into each one of them, but each one of them has been fairly well understood, at least for all practical purposes, though there can be a lot of pure academic research in each one of them. But where it really matters to the industry is in combining these. If not all 4, at least 2 or more of them, you're trying to combine to see what is the overall effect that is happening. So we'll go into the last 2 in the next class. Thank you.